Come on, guys. Someone out there knows the answer to this. Why would I want to separate space-time? Have you ever had to use somebody else's model and figure out what dimensions their model were? And you couldn't figure out whether they were meters, miles, what time scale they were at. You couldn't add a new class because you didn't know how to deal with what the scale was with time and space. This is going to help me get around that problem. I know where to look and I know how to find this stuff. And then finally, if we're looking at research, we're going to have some input parameters, right? So this is the output. What are we telling, what are the parameters for what our population looks like and when the bomb goes off? So that's in a separate class of its own, so we can control this later and let this run and be our experiment. And so it starts to look like more of a classic scientific experiment where we have controlled variables, we have some independent variables inside the model, and then we have outputs. And then finally, I decided that it was getting really hard to figure out what I was looking at. So I created a monitors class where I can pull out all the data that I want from the agents, from the model. So what agents were commuting, what agents were at home or at work, and how many agents have died after the explosion. So this is my architecture design. This is the ideal representation of what's going to happen in my model. And they're pretty much kind of instantiated single classes without too much interaction. So if I change something in one, it shouldn't hugely impact the other. Okay, good. I've got a goal, I've kept it simple, and I have a design. I should be all set. Oh, shoot. Garbage in, garbage out. All right, guys, if your parameters is junk, then what's going to come out of the model is also junk. So we need to make sure we're applying solid theory. We're not just making up the processes as we go along. And we also want to use empirical data. Now, as a modeler, you're not going to go out and do field experiments. You're going to depend on other people for your data. So you want to make sure it's good quality data. And I'm not going to go into what that looks like. That's a whole other talk. But that's modeling principle number 4. So what we did for that is we took census data, and we took school data from the EPA Office of Environmental Information, and we also got sensor tag or shape files to get the data for our roads and our population. And this covers the movement of where our agents are. So we have the population makeup, and we have workplaces, and school places, so we know where they're going to be. This is what the study area looks like with all the roads. So these are the roads that are mapped into the model. And from the census data, we created a synthetic population. And from that synthetic population, we were able to put homes, workspaces, and schools all along the road networks. And from that census data, we were also able to derive networks. So we see an example family network with the work ties in green. Actually, this isn't one individual family network. So we have the green ties or the work ties and the blue ties or the school ties. All right, good. We actually have the building blocks of our model. We've used empirical data to derive the dynamics. What next? Verification and validation. You need to confirm that ABM is performing as you designed it and coded it. This means that it's doing what you think it was supposed to do. This doesn't mean it's right. It just means your ideas, your design are right. And then we need to validate, and we need to make sure that it actually accurately represents the real world. This is the last modeling principle that I want you to walk away with. And what we started to do, what we've done thus far is verified and validated as much as possible the population, the distributions of how many households there are with children, with seniors, what the average family size looks like, and what the average household size looks like. And we're pretty close to the real census data. We also looked at the degree distributions of how many network ties agents have at home and at work and at school we used a small world algorithm to design how many agents, what the networks look like for each individual agent in those locations. So we thought this is looking pretty good. Our data looks good. What about the model? So So we have a basic model set up. This is just a snapshot of the model, smaller space. And we can see agents starting to commute here. Most of the agents go to Manhattan. So I don't know if you're aware of this, but Manhattan doubles in size. It goes from 1.5 million to approximately 3 million people. And when we look at them commuting in, we can start to see them all floating into Manhattan. So visually, we can use the UI, the user interface, to kind of test whether the model is doing what it's supposed to do. Now, for the exciting bit, a little bit of progress. What we've done is, this is a model with a larger sample size. How many is 23,000? Yeah, 23, right?
Yes.
23,000 agents in this
I
case.
thought it was 260, but maybe 23.
I think it's 23,000. And then this is after the bomb goes off, is a snapshot, and you can see the rings. White indicates the agents died. Darker purple indicates that they're more injured, severely injured, and blue, less injured. And you'll notice there are red dots in here. That is intentional. What that means is that some of the agents survived. So even in the closest, this intermediate ring here, not the center, there will be people who survive because of where they're located in the infrastructure and in their buildings. So we've visually verified and validated what we know of nuclear bombs, and we said so far our model is doing what it's supposed to do. So we've got a model, right? We're only part of the way there. We've demonstrated that we have a population, we've integrated networks, we've shown spatial effects, we've allowed for some exploration. We have a lot more work to do. We need to add now the group and network dynamics after the detonation of the bomb. We need to continue verifying and validating this behavior. We're going to have to apply this to a larger region, because right now it's just the New York City commuting region. And we also want to add some greater cognitive behavior and improve the fidelity, and then get to full-scale experimentation. But what I want to do is kind of leave you with these principles. This will help you get a model in place that you can actually use and potentially build off of for future research. And with that, I have to thank DITRA for funding us. Thank you guys for listening to me. And I open up for questions. It all made sense. There were no questions. If you have questions about problems I ran into, yes.
Sure. Did you get traffic jams if everybody tries to go into the same place?
Traffic slows down. Our current model has not calibrated to the actual time it takes for the commute to take, but it will be calibrated with traffic. Yeah.
So what are some of the factors that were involved in the survivors within the closer radius?
Well, being underground and covered in cement protects you from radiation. That's one example.
Subway?
Yeah.
Okay.
Yeah. There are some nuclear fallout shelters still in New York. I don't know how accessible they are, but they are on a map somewhere. Yes.
Once the model is working, what are you planning to test for?
So what we want to show is how agents form groups, and how forming those groups with different makeup of who's in the group will affect survival and where they go. So what decisions do they make? Do they decide to go home? Let me go back to the map here. Do they, when they're over here and they live uptown, do they cross through this area, or do they decide to go around? So some of our decision making when we're under stress is not the best. So we're going to see a lot of variety of decisions. So a smart person who's thinking is going to take the bridge or the ferry and maybe go the long way around to get home. Someone who's not thinking runs into somebody who's injured might actually decide to come a little closer in where maybe there's a medical station or something. So the question is, when we know where the hospitals are, when we know, the question is, how do these people actually behave with the multiple decision-making space that they're going to run into? This is without any decisions. They're not going anywhere after the bomb. And we don't know how that aggregates up into a larger scale situation. So the first question is, what do they do with just the basics? They want to get home and they want to be in a safe place. What does that look like when you're scaling up to 24 million people? And then after that, we can look at, okay, if we station medical people here, if we have people with training, better knowledge of how to behave, to improve their survival outcomes, does that then change how they behave and where they go in groups and then improve survival outcomes? It's kind of like training for survival with the first shooter training. If anybody's gone through that, that'll wake you up. Did I answer your question?
Do you have a favorite hypothesis you want to test for?
I think embedding some of those skills will improve the outcome, but until I start seeing what the basic group dynamics are with what that'll look like at that scale, I'm not ready to put a hypothesis in place for testing. So this is just building the experiment control space, and then we need to start actually building in specific test hypotheses for the model. Oops, sorry.
Yeah, how would you plan to do the validation and verification of a model this complicated with hopefully,
I built a simple model. Did you see that? See how it got complicated really quick?
I think your parameters and agents have.
Right, right. So one of the things that we can do is we can sample our 24 million population to scale that down and do a lot of our testing on smaller size populations. We can do a lot of runs there and then see if that holds true for a larger test run with all 24 million agents. That's one thing we can do. I mean, we're never going to be able to validate because nobody's tracked a nuclear bomb in New York City. What we can do is we can look at evacuation data, we can look at disaster data and see how people behave in similar incidents. So earthquakes are a really good test case to validate behavior in this kind of situation. And I'm working with some people at the Disaster Research Center in Delaware and hopefully some people out in Colorado at their hazard center to see and get some of that data in the future. Anybody in the midst of programming having any stories they want to share, ask me how I solved those problems.
Another question, I'm just curious, do you know of anyone who's modeling what occurred in Paradise, California with the wildfires?
I don't, but I bet I will learn and meet a lot of them at a conference I'm going to in March.
That might be
Yeah.
We gotta.
But I know that there are some wildfire experts who model that for firefighters, so I'm sure they're working on that.
Oh, I got Steve, I never pronounced his last name, Gurin, the Redfish group who hangs out in Santa Fe Institute. They used his stuff to help help the firefighters when they were trying to get there. So he's probably got lots of insight into that.
Yeah, they have a tool called SimTable, which helps firefighters plan how to set and fight the fires and play that out. It's really, really interesting technology if you want to check it out. And this, we're taking this beyond fire, so it'll be interesting to see if we can use the human behavior to improve SimTable and these other types of models.
Just a funny story about SimTable. Recently, so they used, it's basically a big table with a projector on top. You put some sand on there, and you can put the topology of the space that you want to look at. Kind of project it down. You can look at what the wildfires are. Well, with the recent wildfires, they were mainly using the SimTables out in California for training purposes. But the fires got so bad that they moved all the SimTables that they had to the operational centers late last year, and they're using it directly to combat all the wildfires that are happening right now. And that was published in, I think, like Popular Mechanics or something. I didn't even talk to Steve about that. I saw that pop up.
Yeah, well, I just have my 2 cents back since we have so much time. I want to get back to commenting and documentation of your code, so I'm in the process of kind of backfilling some of my comments. So try to do some of that along the way. It makes documentation easier. So for example, I now have an architecture drawing, so I'm making a start at that.
You might want to also mention that even though Mason might be developed by professional computer scientists. They're not infallible for making mistakes.
That's right. The other thing to keep in mind, this isn't robust code. So we're building on top of code that's changing and depending on other code that's developed by other developers. So Mason is dependent on Vivid Solutions set of libraries. We're using Java that gets updated all the time. So every time Java gets updated, there's a chance that Mason won't work. So your own code is dependent on Mason, which is dependent on GTS, which is dependent on Java, which is dependent upon a lot of other things that are changing as you're designing it. So over the months that you design your ABM, you need to be prepared for some of these changes. And then it's not you, it's just that's part of software design, which is why we can go all the way back to our beginning. And hey, do you guys want to see the model?
Yeah.
Oh, come on. Let me do this. I've lost my cursor.
You went off screen high.
Hi, thank you. Okay, so at the start of the model, they're at home sleeping. And then they're going to wake up and they're going to head into work.
They're quick.
Yeah, they're very fast right now because it's a small sample size. And then they're going to go home at the appropriate time. They cleared out pretty fast. And then they're going to go back. Aren't we all? So this is a working model. And yes, I'm brave enough to share this with you live and in real time. I should get credit for that. The bomb went off, so you'll notice that we don't have any white dead agents, so I haven't merged Bill's code in with this yet.
Right.
Very good.
Yep.
So, there we go. That's all I have, folks. I want to get you out early. 45 minutes.